Hey everybody, welcome back to another chemistry lesson. This lesson is the atomic knowledge timeline, where I talk about how we got to the knowledge that we currently have about atoms. So the atom is the smallest identifiable unit of an element. There are 91 naturally occurring elements and then over 20 elements that we have created synthetically in a lab. And we are now at the point where we can actually look at atoms using a scanning tunneling microscope. We can look at the atoms individually. And the example here on the right-hand side is some, I believe, Chinese. Sorry, whatever language that is, I don't speak it. So, but some letters that were created. They are iron atoms that are in red on a blue surface, which is actually copper. And this is made by a scanning tunneling microscope. And the cool thing is that IBM has actually created a stop motion video using a scanning tunneling microscope and manipulating the atoms to make that movie. Now, I'm not really sure why, but it's not letting me play this video for you. So it's called A Boy and His Ball. You can look it up. It's this boy playing soccer with that, and each of these dots that you can see is an individual atom, which I think is super cool. All right, so the idea of the atom began way back, like BC era, 2,500 years ago almost, with Democritus. So he was the first guy to use the term atom and proposed that matter was composed of small indestructible particles. This was opposite of what the famous Plato and Aristotle thought, which was the fire, air, earth, and water business, making up all of creation. So this was a distinct, branching off from the commonly accepted thought. So there are three laws that led to the development of atomic theory as we currently know it. It's the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. So first, the law of conservation of mass, which was formulated by Antoine Lavoisier, a French scientist, and it states that in a chemical reaction, matter is not created or destroyed. So what that means is when we have a chemical reaction, we're not getting rid of or making new stuff. All we're doing is rearranging what we already have. So practically speaking, in this class, when we have a chemical reaction that occurs, our total mass of our products has to be the same before and after, right? So we have to have the same amount of reactants, same amount of products. So mathematically equals, okay? So you can see here we've got 7.7 grams of sodium, 11.9 grams of chlorine gas for a total of 19.6 grams of reactant. These two things react, we get sodium chloride or salt, still 19.6. So 19.6, 19.6. So this was the first law. The next thing was thought of by Joseph Proust, which was the law of definite proportions, saying that all samples of a given compound, regardless of where they come from or how they were made, have the same proportion of their constituent elements. So what that means is every water molecule, for example, no matter where it comes from, no matter how it was made, is going to have 2 hydrogen atoms, 1 oxygen. And then finally, John Dalton, who was the first atomic theorist, we'll talk about him in a minute, had the law of multiple proportions, which is basically just saying that atoms can arrange and bond to each other in different ways. So an atom of A can combine with atom or atoms of B to give us AB, AB2, AB3, etc. And we can also look at this by mass. So a specific mass of carbon to a specific mass of oxygen, for example, here. So carbon dioxide has 1 carbon and 2 oxygens in it. We can look at it that way, so a 1 to 2 ratio of carbon to oxygen, Or we can look at it in a mass ratio, 2.6 grams to oxygen to 1 gram of carbon. So 1 to 2 or 1 to 2.67, depending on what we're looking at. And then likewise, on the other side of that, carbon monoxide, so carbon bonded to 1 oxygen, is 1 to 1 or 1 to 1.33, depending on what we're looking at, mass or number of atoms. All right, so about Dalton. He basically had the first, what we know of as an atomic theory. And he explained that matter is composed of tiny, indestructible particles called atoms, and that all atoms of a given element have the same mass and other properties that distinguish them from the atoms of other elements. Atoms combine in simple whole number ratios. That just means we don't have half of an oxygen. It's either an oxygen or it's not, right? And then atoms of one element cannot change into atoms of another element. In a chemical reaction, our atoms are only changing the way that they're bound to each other, and other atoms, not what they are. So as you probably guessed, based on the fact that I called Dalton the first atomic theory, he got a few things wrong. So there were scientists that came after him to try to sort of work out the kinks of his theory, right? And so the first one was J.J. Thomson, who used a cathode ray tube, which we see drawn out here, or an actual one here, and he ended up discovering the electron. So the tube is sort of, evacuated. We suck all of the air out and then pump it full of a gas. And then on either end, you can't see it super well here, but on either end we have these metal plates and then a current, an electrical current that runs through and creates a current, right? And then out of that we get this beam here. It almost looks like a laser coming through. And no matter what gas was in the tube, no matter what metal he used for the cathode and the anode, the behavior was exactly the same. We had this beam, and when he exposed the beam to a positive charge, the beam would be attracted to the positive charge, right? And then likewise, no matter what it was made of, if he exposed the beam to a negative charge, then he would see that the beam was repelled by the negative charge. Did not matter what it was made of, the same exact behavior every single time. So we all have heard the saying that opposites attract. It's true. So based on that fact, Thomson knew that because it was attracted to the positive charge, the beam itself had to be made up of negative charges, the opposite. So he found that, as I said, they carry a negative electrical charge, but he also found that they travel in straight lines and are independent of the composition of the material. So again, doesn't matter what it came out of, what gas is in there, what metals make up the cathode and anode, it's all the same. So Thomson has now discovered the electron. That's the name that he gave it. And this is a negatively charged, very low mass particle that is present in all atoms. That's why no matter what material he used, he always got the same result, right? So with this knowledge, we know that matter is neutrally charged. And the reason we know that is if it wasn't neutrally charged, we would be electrically shocked by literally everything that we touched. So neutrally charged matter, right? So he knew that if we were pulling the negative charges out, then the positive charges had to remain, right? Because positive plus negative equals neutral. And so this is where he came up with the plum pudding model, where electrons were embedded in this like solid sphere of positive charge. And he was British, so plum pudding is like a bread type thing. Think of it like a blueberry muffin, right? With the electrons being the blueberries kind of stuck in place. and then the muffin piece itself being the positive charge that's left behind when those electrons move. Next up is Robert Millikan. He performed the oil drop experiment that he became famous for, and he discovered the charge of a single electron. So I don't fully understand how the mental gymnastics he went through to get to, hey, this is a good idea. But what he found was he used an electric field that he set up here to control these oil drops that were falling, right? So they were falling between the positively charged plate and the negatively charged plate. And he knew the mass of one drop. He knew the charge of one drop. And by using radiation and a light source and a microscope and some, fancy measuring tools, he knew that charges always appeared in multiples of negative 1.96 times 10 to the negative 19th coulombs, which is what we now know to be the charge of one electron. And then, by using Thomson's mass to charge ratio for an electron, Millikan figured out the mass of a single electron using that charge that he discovered. Then came Ernest Rutherford, who performed a very famous gold foil experiment. And his goal when he went into this was to confirm Thomson's model, right? So what he had was a piece of gold foil in the middle and this detecting screen around the outside, and then a lead box that he would shoot alpha particles out of. Now, this detector screen would light up, as you can see here, would light up whenever the alpha particles impacted it, right? So he got some really unexpected results. What he expected was that all the particles would go straight through the foil, because if you remember, we had this even distribution of very tiny particles in this mass, so none of them should be big enough to deflect the alpha particles. However, even though most of them went straight through, about 1 in 20,000 actually bounced back towards the source, which means that there's got to be something big enough in the middle of an atom to actually impact the trajectory of that. And Rutherford was known for having said that the results were so unexpected, it was, and I quote, as if you had fired a 15-inch shell at a piece of tissue and it came back and hit you. So imagine like a bowling ball made out of solid metal shot at a piece of toilet paper, right? That's how unexpected it was for that like beam to not go through the foil, but rather to hit it and bounce back. So very unexpected results. So again, Rutherford thought that these little tiny particles weren't going to be big enough. It was going to go straight through all of them. But what ended up happening was there was a chunk in there that was big enough to deflect. And this is how we discovered the nucleus. So there would have been no deflections. Because there were, he knew that we had to have a large region of empty space that had a small region of very dense matter, dense enough that it was going to deflect. So based on this idea, Rutherford came up with what he called the nuclear theory of the atom, with basically 3 parts to it. First, most of the mass and the positive charge are in the nucleus, which is at the core of the atom. And then most of the volume of the atom is empty space, because we know that electrons are very tiny. And then the tiny electrons are just kind of flying around. The third piece is there are as many negatively charged electrons outside of the nucleus as there are positively charged particles, which became named protons, within the nucleus, so that the atom is electrically neutral. So this is where we came about our knowledge of the nucleus and the proton. And then finally, James Chadwick was his student, actually. that came along and discovered the neutron because he knew that this model that Rutherford had come up with was great, but didn't really account for all the mass of the atom. So our final subatomic particle, the neutron, was discovered by James Chadwick to account for the mass that was previously missing. So our neutrons weigh almost exactly the same as a proton, but it doesn't have a charge on it. Neutrons are neutral. So here's what we know so far. All of our atoms are composed of these same subatomic particles, and protons and neutrons have nearly identical masses, and electrons weigh a fraction of that. So this is 10 to the negative 27th kilograms, very, 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 very tiny. And you can see that it's out here at the third decimal place in that scientific notation where the difference is in their mass. So they're very, very similar. And also want to point out the gigantic difference between these two and the electron. So all together in one pretty little package. What we use, because this is a ridiculously small number that nobody needs to worry about memorizing, this is what we are going to use. It's called an atomic mass unit. And we basically say that protons and neutrons are one atomic mass unit. And then relative charge, protons are +1, electrons are -1, neutrons are 0. And then if we want to talk about actual electric charge, here you go. Now, this was not the end of our atomic knowledge journey. Next, we had this guy named Niels Bohr that came along, and he said, the nuclear model of the atom explains a lot about what happens, but it does not explain structural changes that happen when we're gaining and losing energy. So Niels Bohr developed a model that explained those changes because atoms do undergo energy transitions. It's the reason why if you ever see a blacksmith working on like a horseshoe, the horseshoe is literally red hot because there are energy transitions that are happening. And that's something that we discuss later in the course. But this model that he came up with was the planetary model. So it wasn't just electrons, willy-nilly outside of the nucleus. It was electrons in these set orbitals that have set amounts of energy. All right, so we know that protons and neutrons are together in the nucleus. Sorry, this is too cute. I had to. Are together in the nucleus, and they weigh approximately the same, so one atomic mass unit each. And this is how we calculate an atom's mass. This is important later, as in when we work on things in class. This is important. And then we know that the electron is outside all by his lonesome. Look how sad he is. Electrons are outside the nucleus in complex orbits, and there's more to it. So the current model is the quantum mechanical model, and this was come up with. Okay, sorry, you saw me have a total brain ridiculousness. Erwin Schrödinger came up with the quantum mechanical model, and it is a complex equation with wave functions and all sorts of stuff. We do get more in depth into this whenever we talk about the electromagnetic spectrum and all of that, but for now, all you need to know is that this model helps explain how and where electrons exist. It helps us predict properties of atoms that are directly related to the behavior of their electrons, and his equation, the equation is literally just a probability equation. It helps us find the probability of finding an electron right here at any given point in time. It does not say that there's a specific path or anything like that. It's more than that. And again, this is something that comes up later in the course. But the general idea of this model is that you're more likely to find an electron closer to the nucleus than further away from it. A lot of times you'll see, if you see a drawing of this model, it'll just be a fuzzy ball that is darker in the middle and lighter on the outside to show that you're more likely to find electrons in the center than you are around the outside. And there's a lot more to it, but that's a discussion that's more appropriate to electromagnetic spectrum and other applications. So we'll go into it in more detail later. No, you will not ever have to do this math, just unless you go into, quantum physics or something. But anyways, that's it for our atomic knowledge timeline.